Hi everyone, this is the second part of my lecture course Statistics for Everyone towards Data Science with R. Start off with some definitions. Population, the complete set of elements under study, for example, the all people of a country for an election. Sample, some randomly selected subset of population, like a part of a city or a county or some people gathering in some intersection or street. Census is different from sample, collecting information from every member of a population, which can be very costly and time consuming. Survey also is different from the other one, Cody in order to collect data for the analysis of some aspects of a group or area. Population versus the sample. When we're talking about the variables of a population, we usually use parameters, which is a characteristics of a population. In contrast, for the random sample or variables of a sample or random sample, we use statistics, which is the characteristics of a random sample. Two types of data, qualitative and quantitative. Qualitative or categorical data, which are non-numeric, such as gender, color, ranks in a running race, names, religion, and zip codes, where the mathematical operations are meaningless. In contrast, for the quantitative data, which are numerical, such as wages, heights of everything, weights of everything, temperature, time, speed, distance, where the mathematical operations are meaningful. Two types of quantitative data. We have two types of quantitative data. The first one is discrete, which can be in two types itself. The part A is discrete data, which can be finite, like the face of any regular three-dimensional solids except a sphere. We have the tetrahedron with 4 faces, cube 6 faces, octahedron 8 faces, dodecahedron 12 faces, iso- icosahedron with 20 faces. Also, we can have a solid with 100 faces, which is in the bottom left picture, and 10,000 faces, which is on the bottom right pictures. Part B is infinitely countable discrete data like the counting numbers 1, 2, 3, and up to infinity, or integers which contain natural numbers, counting numbers, plus 0 plus the negative of natural numbers. There's a natural question arises here. Is there anything in the real world as a real subject or real object that is infinitely countable? How about the particles in whole worlds? The commonly accepted answer for the number of particles in the whole world in the observable universe is 10 to the power of 80. This number would include the total of the number of protons, neutrons, neutrinos, and electrons. Even the number 10 to the power 80 is a very, very large number, but again is a just a finite countable number. So the particle also countably finite. How about the number of the golden state arcs? As we see, if we start from the top going to down using this golden stage, how long it takes to go down and down and down, we don't know yet. The second data is continuous data, which is uncountably infinite, usually a measurement such as time, weight, height of any object, and comparing to three-dimensional solids in finite cases, the whole points of a sphere may be a good example. The values can be any real number in the set R equal to the interval from infinity to minus infinity to plus infinity. Also, another example, which is the continuous numbers, which can be seen in the Michelson's speed of light experiment. All the numbers measured speed of light in 1000 kilometers per second. We have the numbers with integer part, also the decimal part. So these whole numbers are considered as continuous numbers. Four levels of basic measurements scales, the process of applying numbers to objects according to a set of rules. Nominal or categorical, not ordered, such as gender and religion. One can assign numbers like male equal to 1 and female equals to 2, which has no real meaning other than differentiating between objects. Ordinal, which can be ordered, but the differences are meaningless, such as ranks in a running race. First, second, third. Interval, which can be ordered and the differences are meaningful, such as temperature in degrees Fahrenheit. Differences between 65 and 64 is the same as 43 and 42, but no natural zero. Zero does not denote absence. 0 degree, no true 0 point. Ratio. Ratio, just like interval, and there is a true natural zero such as height. For example, 100 divided by 4 is equal to 25. So 4 times of 25 is 100 in meters. Zero height, like ground zero, zero gross, it shows that it does denote absence of. Design of experiments and observations. Experiments versus observations. Experiments. Apply on a treatment and then measure the effect on the subject. For example, drug treatment, which usually is a test on mice before testing on humans. Observations. Measures specific specific features but does not modify the subject. Opinion polling for an election, asking someone how do you feel for some party? How do you like a movie? How many are females in this course? Random. Each member of a population has an equal chance of being selected in a sample. Simple random sample. Each group of size n has an equal chance of being selected. Four common sampling techniques. Convenient sampling. Use the results that are easy to get, not random. For example, we can go to a park and just ask opinion of the people gathering in a park, which is not random people. Systematic sampling. Put population in some order and select every 13th member. Stratified sampling. Break population into subgroups based on a character. Then sample each subgroup. Cluster sampling. Divide population into clusters regardless of characteristic and randomly select a certain number of clusters. Then collect data from the entire cluster. Cluster sampling versus stratified sampling. Cluster sampling, cheaper, usually not representative of whole population. Stratified sampling, sample more representative, good information on subgroups. Example for stratified sampling. Foot measurement study of the population of Taiwan. Total sample size of 1,000 from I don't know how many the population is. Sample for each category selected randomly from population. First, we divided in terms of age group, ages from 0 to 4, and then age 0 to 4 consisting of 830 male and 772 female. And from this, we have chosen or we have randomly select 41 male and 38 female. Likewise, from the bottom one, 50 plus ages, which include male of 1882, 1618, we randomly select 94 from male and 80 from female. And then we get the total of each sample, male and female. We got total of 79, 97, 99, 90, 193, 268, 174, and this add up to 1,000 of population, actually 1,000 sample size. Probability event, a collection of outcomes of a procedure. Simple event, single outcome. Sample space, all simple events, every possible outcomes denoted by S. As a matter of fact, every possible outcome means all possible outcomes denoted by S, not just one individual. Random variable function from sample space into real numbers denoted by X. Here we have a graph, this rectangular shape, and this white spaces is some samples, different samples, and then X takes these samples to 0, 1, and 4. And this whole thing is called sample space, and the S1, S2, and S6 are different randomly chosen samples. For example, random variable is function from sample string to real numbers denoted by X. Probability, likelihood of an event occurring denoted by P. Likelihood of an event occurring or happening, which is denoted by P. For example, P of X The random sample of S3, which maps to 1, is equal to 1/6. Means that probably the area, the relative area of the random sample S3 with respect to the whole area of a rectangle is equal to 1/6. Note, the random terminology is coming from the random procedure experiment. Means that the experimental procedure is random because uh, because of that we call random experiment or random sampling. Examples: flip a coin 3 times. X function which map from this space of coins into real numbers. X for any event gives the number of heads. So the sample space is can be 3 head or 2 head, 1 tail, 2 tail, 1 head, and so forth. And if we see from the right hand side graph, we can see that we can get for the value of the function x numbers of 3, 2, 2, 1, 2, 1, 1, and 0. So this is the sample space, and then we have the number of uh, number of heads. In the second example, we roll a white die and a red die, and we get the pairs of getting numbers from 1 to 6. And if we write down all these numbers, we can get altogether 6 times 6, which is 36. If we pick randomly one of these events, the probability of selecting only one event is equal to 1 divided by 36. If A is an event, then P of A is by definition is the equal to the probability of event A happening or occurring. 3 types of probabilities. Observed probability. Probability that is estimated based on observation. It happened. We do some experiment and we observe something happened, and then we can calculate the probability of that event which is happening. So, and probability is equal to number of events that happens or occurs divided by number of the time that procedure was repeated, all the events. Classical probability based on chance of an event occurring, which is called theoretical probability, should happen. In this case, probability of A is equal to number of ways an event A could occur divided by number of simple events. Subjective probability, educated guess such as accident or getting sick. Disjoint or mutually exclusive events. They don't happen at the same time. Complementary events. Events which are mutually exclusive and the union make up whole sample space. Complement. The complement of an event A is denoted by A C or A complement, and is the event when A happens, then A complement doesn't happen. Compound event. An event when joins 2 or more simple events. If A and B are disjoint, then we have P A union B is equal to PA plus PB. Examples. Example 1. The probability of selecting a heart from a deck of cards. We know that the number of heart is 13, and the whole number of cards is 54, so P of heart equal to 13 divided by 54, which is 25%. This is classical. Example 2, flip a coin 50 times and get 45 heads. Then probability of getting head is equal to 45 divided by 50, which is 9% observed. Example 3, how hot is there in June in Toronto? Educated guess. We don't know for sure. Example 4, a baseball player passed the ball 128 out of 200. The probability of passing the ball is equal to 128 divided by 200. This is we observed. Example 5, opinion about the movie. 120 people said that they love the movie. 800 said they hate it, and 30 no opinion. If we go out and ask a randomly selected person and if he says he loves, then the P probability of movie good is equal to 120 divided by 120 plus 800. Of course, we have here plus 30, not 3. So this gives us the probability of how favorable a movie. Example 6, find the probability that if a family has 3 kids, and if we assume that 2 of them being boys, assuming equal chance. Having 3 kids and 2 is boy can be boy, girl, boy, girl, boy, girl, boy, girl, boy, which is classical. And probability of A is 3 out of 8 cases, which is 3 divided by 8. Conditional probability. Probability of B occurring given that A occurred is equal to P of B and A at the same time divided by P of A. Independent events. If and only if we have P of A and B is equal to P of A times P of B. In tossing a fair die, for example, if we have A equal to 2, 4, 6, and B is equal to 1, 2, 3, 4, then A and B is equal to 4. So P of A and B is equal to 2 divided by 6. P of A equal to 3, 6, which is 1 half. P of B is equal to 4, 6, which is 2/3, and we have 1 half times 2/3, so it is equal to 1/3. And 1/3 or 1/3 equal to 1/3, so and so A and B are independent. Remark: if A and B are disjoint events with positive probabilities, can they be independent? No. Example: since P of A times P of B is positive, yet P of A and B is equal to P empty set, which is equal to 0, because we set disjoint, so P of B and B is empty set, and the probability empty set is 0, but P of A and PB is positive, so they are not equal. Okay, I think I leave it there, and thank you very much for watching, and please give your comments, and I will start the R coding for or preview the introductory parts of R coding before going to the uh, all parts of this two sections in detail. Thank you so much, and see you again next time.